In previous chapter, we understood that virtual memory gives each process illusion of large and continuous memory space. But how does the system actually translate virtual address into a physical one? As you can see here, we have virtual memory at top and physical memory at bottom. And something in between is responsible for mapping them. That something is page table. Let's take a real example. Suppose CPU generates this virtual address 0x764. It searches the page table. First entry not match, second entry no, still no match, and finally it is 764. It maps to physical address, and once we found it, we activate the word in physical memory. That's how translation works. Simple, direct, but now we have the problem. Right now we are mapping memory word by word. Every tiny block you see here needs its own page table entry. If you want to access address 512, we need an entry. If you want to access 786, we need another entry. Everything in between we also needs entry. This might look manageable here, but what happens when we scale? How many entries do we need to map the full 32-bit address space? That's 2 raised to power 32 bytes, which equals to 4 gigabytes, and each word is 4 bytes, so number of words addresses is 2 to the power 32 divided by 4, that equals to 2 to the power 30. That is around like 1 billion entries. What if each entry takes 4 bytes? That's roughly 1 gigabyte for page table. 1 gigabyte just to store the mapping. Our RAM will be full. This is not scalable. Now you might think, why not just store the entries for addresses we use? If the CPU tries to access memory without mapping, it fails. No mapping, no translation, no access. But when we insert page table in between, now the flow works. CPU, page table, and physical memory. We need coverage. For the entire address space, instead of mapping memory word by word, let's zoom it out. Imagine this table going on and on and on. It's too big. What if instead of mapping individual words, we group them into pages? We don't need word table, we need page table. One page is typically 4 kilobyte. That's 4096 bytes. Since each word is 4 bytes, that means one page contains 1024 words. So now one page table entry maps an entire page. Earlier, one row mapped one word. Now one row maps one page. That means instead of one entry per word, we need one entry per page. Earlier we needed 1 billion entries, now we need roughly 1 million. That's 1000 times fewer entries and page table size. From 1 gigabyte to just 4 megabyte. That is power of paging. But nothing comes free. We could move memory one word at a time. We move entire page now. Even if we only need this tiny word, we move all 4096 bytes. So yes, we lose fine grained control, but we gain scalability and trade-off, and that is trade-off. That trade-off is what makes modern operating system possible. Virtual memory divided into pages. The page table maps those pages to physical memory pages, and that is how address translation becomes scalable. Page makes virtual memory practical, and without paging, modern computing simply wouldn't work. Thanks for watching. If this made things click for you, subscribe the Debug the Dreams for more deep dives into the computer science. I'll see you in the next one. Thank you.